Hi. So in this video, we're going to look into the notion of relaxations used to solve integer programming problems. So we'll look into linear relaxations first, and then we'll briefly discuss combinatorial the relaxations. So linear relaxations are, as the state of the art stands, the framework behind professional code for solving integer programs. And the reason for that is because there is, really mature, well-developed technology for solving LPs, like we've been discussing in the last classes. Perhaps with the most important of them being developments associated with dual simplex and the ability of, from solving an LP relaxation, being able to solve a successive LP relaxation, which is modified only by means of including new constraints, as we'll see in a couple of probably next video. So LP relaxation is basically what is central in the process, in the methods for solving linear programs. So what is that LP relaxation? Well, we can think of our IPs being defined by, like we've seen before, by the intersection of a polyhedral set and a collection, but also subject to be a integer value. So the LP relaxation is simply solving the problem with respect to this polyhedral set only. So basically solving this LP problem, which happens to be this. So here is a sort of a numerical example with a picture so we can understand a bit better what's going on. This is just a problem posed as we've seen before, the main difference, the fact that now we are requiring our variables to be integer. Okay. And the consequence of that in the geometry of the problem is the following. So this picture is showing us this polyhedral set P, which I'm marking with these green lines here. See? So it's this polyhedral set. So if I were to solve, this as an LP, as a linear relaxation, this is my optimal solution right there. Okay. However, this thing is an integer program, and therefore my feasible region is not a polyhedral set, but instead a collection of points just scattered around that happen to lie within P. You see? And several things can be thought about this and contrasting it with what we've seen for LPs. First of all, there is absolutely no guarantee that an optimal solution will lie on a vertex, unless, like we seen in the last class, we have a perfect formulation that happens to be the convex hull of these points. Then this optimal solution, or this optimal solution even, will be a integer point, and that kind of displays the result of what we just see. It so happened that if we have the convex hull and we find this as an optimal solution, say, that tells us, and that solution is feasible for my original problem. And if I look at the objective function of both, because the objective function is the same, notice that we are creating relaxations just by enlarging the feasibility set. So it's also optimal for the original IP. So that's one thing to consider that we're going to use. And then the other thing that to keep in mind here is that there is no such thing as convexity anymore. So if you draw a line between two feasible points, and the points that the convex combinations do not belong to the feasible set, because the feasible set is just these dots, right? Scattered out, separated from each other. Then a reflex some people have when they see that, well, okay, we're using solving LP relaxations. Why not simply, solve the LP relaxation and then just apply some rounding? Rounding is a horrible idea. So you can assemble a few examples. It's easy to assemble example to show that rounding is a bad idea. So in this case, for example, when you solve the LP relaxation, it so turns out that your x2 component is integer. So this solution here is 2.something3. So what you would do is you will just round x1 either to 3, which we can see here that will be infeasible. So it will take you to a feasible solution. or you could round it to 2, which will take to this solution 2, 3. And if you go and solve this as an IP, you can see, as we'll see in the next video, that the optimal solution is actually this one. So by solving this as a LP, and then rounding, you either generating a feasible solution or a suboptimal solution. So it's certainly not a good idea. But it doesn't mean that using LP relaxations is a bad idea. It's just that the subsequent steps of improving the relaxation or using that information to, find primal and dual bounds has to be a bit better thought. But once we can, thinking about dual relaxations, we can have a mechanism more or less to generate primal and dual bounds. So a primal bound can be just trying a point. So you can, for example, try the point 2, 1, which would be this one. And that will give you objective function of 7 for this problem. You can try another one. You can try 1, 0. You can try any of those. And because it's so small, you can actually try the 11 of them and pick the best. Well, of course, this doesn't become, as soon as you have a few more variables, this is just computationally impossible. And this is going to give you a dual bound, because you can see that whenever we solve the LP relaxation, we're getting this value, 8.42, for the solution there. And remember that because we're maximizing, our dual bound is an upper bound. So here it is. Right? You can see that, the solution is very suspicious, right? It almost feels like, because this is the optimal solution for the LP, this should be the optimal for the IP. But if you test the solution 2, 3, you can see that you get 8 minus 3, which is 5, I think, yeah. Which is, already worse than the 7 you got here. So being discrete gives you some interesting capabilities, but at the same time turns the whole process in much more demanding if you try to use brute force or complete enumeration. It's simply not possible because of what we've seen last time, right? But that's the mechanism of a LP relaxation. And that kind of connects with what we're seeing last class when we were talking about the notion of stronger or better formulations. We did see that a better formulation was that was contained within another. So P1 was better than P2 if P1 was contained within P2. And the reason for that is associated with the bounds you're getting from these relaxations. So here is a proposition that I'm not proving. If you have a P1 and P2 to be two formulations for your IP, and we say that P1 is better than P2 if this is the case. And look, what is going to happen is that if you look at the objective value of that relaxation, you would see that that objective function, that bound, is going to be tighter for that has worse. So this is a minimization problem, you see. And basically saying that, so when you're solving LP relaxations, you're getting dual bounds. And what this is telling us that when you look at the scale of bounds, this is at 2 and this is at 1, both LP. And why is it the case? Because the reason why is it the case is that you can use the same concept of relaxation to think that P2 is a relaxation of P1. They have the same objective function, and this encompasses this. Because P2 can be seen as a relaxation of P1, it means that we just proved that this should be the case. So the search for optimal, for better formulations, it builds upon the idea that having tighter formulations will lead you to better relaxations and therefore tighter bounds. And thinking that, solving problems like IP problems is just a matter of successively generating those to converge there, having a better formulation is basically giving you a head start. It's like you starting the race a few miles ahead of everyone else. And that's why having good formulations is so important in the context of solving IPs. And so you have everything you need to prove that, by the way. It's just use the notion of relaxation just by simply saying that P1 or even P2 can be seen as a relaxation of P1. So this is the main message that we are trying to convey. If P1 is a better relaxation, it's going to give you better bounce. And that's something you want, because what we're going to see in the next video is that solving an IP is nothing more than a successively obtaining improved relaxations for your problem and solving it, but doing it in a iterative and enumerative way. So the better the relaxation you start with, the less enumeration you have to do, and less enumeration means less LPs to solve, and solving less LPs means solving it faster, more efficiently, and so on. All right. Another type of relaxation that we're not going to explore much in our course, but I thought it was worth mentioning because this is really important in context. This is where you're solving challenging combinatorial optimization problems. So there is this notion of using combinatorial relaxations, which are basically combinatorial optimization problems that can be seen as relaxations of other combinatorial optimization problems. I wanted to mention this in the perhaps most relevant context I've seen this being used, which is the problems relating with traveling salesmen or vehicle routing. So, for example, very simply one very simple relaxation we already see, combinatorial relaxation we see, is the notion that when we posed the traveling salesman problem, and then we started, with our naive way of writing just the incidence constraints, we said, oh, this is exactly like the assignment problem, but there was something missing and we had to add more constraints, right? So you can think that the feasible region, let's call it X, of the assignment problem, just to make sure I'm writing on the same line, it contained the feasible region of the TSP. Because the TSP was the feasible region of the assignment problem plus the constraints that removed subtools. So the assignment problem can be seen as a dual or combinatorial relaxation for the TSP. And therefore, remember that we generate minimum cost tools. If you look at an assignment, there's going to be quite a few subtools there for sure. That's going to be a dual bound, so from below. So, one way is you can generate, and we kind of, played with this idea when in the exercises for the TSP, where solve as an assignment problem, check if there are subtools, add constraints, solve again as an assignment problem with these new subtool elimination constraints, and keep doing that until you find a feasible solution. Because this is a relaxation, and once you find a feasible solution, we can once again use that proposition to show that this is an optimal solution for the TSP. So that's why I wanted to mention that. But this is not it. This is a whole realm of study that's really interesting and very, very, it's still very lively, because these combinatorial optimization problems are, as it stands, a challenge for modern IP technology. One idea, for example, is how can you find even better relaxations? One idea of finding even better relaxations is to look at the notion of trees in graphs. So think about the symmetric traveling salesman problem. Symmetric because it means that going from node I to node J, so costs us Cij, and that's the same as Cji. So going one way on another is the same cost. And we're still trying to find this minimum way too. And so basically, this idea, with this in mind, we can kind of come up with a sort of a stronger relaxation for the traveling salesman problem that is based on the notion of the trees. So one thing that we know for sure is that, thinking of node 1 as our origin, any tool you make is going to have two edges adjacent to node 1, because it's going to be so this is the node 1 where you started, you going somewhere, and then you do a tool, and then you arrive back. So that node 1 is going to have 2 adjacent nodes. Edges. Sorry. Edge is the same as an arc. So we can say that this path is a special case of a tree on an arc. So just a quick definition of what is a one tree. Basically, a one tree is a tree on a graph where one of the nodes actually has 2 edges. By the way, what is a tree in an arc, in a graph? So basically, if you have a collection of nodes, okay, in your graph, and then what you do, you have somehow representation that connects all of them. So that's what you call a tree. And a one tree would be, if this is node 1, would be something that looks more like, and put those in green, like this, for example. And then we can even get rid of that. So so a tree is such that you have, n minus 1 edges, and all nodes are connected. So here we have 1, 2, 3, 4, 5, 6 arcs, and 1, 2, 3, 4, 5 edges. So basically the notion of one tree is that we'll have these 2 adjacent arcs, and then a tree on nodes 2 to 5. So notice that there's an edge missing here for one tree, by the way. We need something that actually looks like this, because we assume that for nodes 2 onwards, so this is a tree, and then node 1 has such. So here is a picture that's better drawn. So this would be a one tree. And you can see that how this also forms a relaxation for the TSP, right? Because this has 1, 2, 3, 4, 5, 6, 7 arcs in 8 nodes. So that would form a tour if they were not having subtours, right? So basically the idea is that 1, 2, 3, 4, 5, 6, 7, 8. Yeah, now that's correct. 8 arcs and 8 nodes. Sorry, I missed one. So basically what you want to do from this is solving this as a relaxation. You can then start, imposing conditions that break, say, this subtour, and then solve it again. But the reason why you are interested in these, or even in the assignment, but this particular, is that there are really efficient methods that can be employed to generate trees that are not necessarily mathematical programming. So you have heuristics that can be made efficient with appropriate computation of structures and so on, that you can keep building these. So basically you can optimize this without even using an optimization solver. You can basically, implement a good one tree generation algorithm and implement a method that can identify a subtour and add a subtour elimination constraint condition on your one tree generation method. That's a way to eventually find an optimal solution. So so that's the sort of idea that we're going to be looking into, how to further generate constraints. Of course, this is much more problem specific. It can be made really efficient depending on specific problems. But for IP solvers, which are meant to be general solution technology, it basically means that we only employ linear relaxations, which are much more general. And of course, you can also solve, the TSP using linear relaxations, like we showed, solving the TSP using branch and bound and so on. But it's simply not the most efficient way of doing it. All right, I just wanted to make sure we actually mention combinatorial relaxations. So coming next, we will look specifically into the branch and bound method, see what is the main features it has, and make sure we'll also have an example, a numerical example, to make sure we understand how it proceeds. So see you in the next video. Bye bye.